Okay, so we need to find the area of the region bounded by y equals x squared, x plus y equals 2, and the x-axis. One thing that I want to note is yesterday we talked about the fact that you're supposed to ignore the x-axis and the y-axis when you find the bounded region. And usually you do, and that throws some people off sometimes. But on this particular question, they're asking you to include the x-axis. You're still ignoring the y-axis, but you are going to include the x-axis in your bounded region. Okay, so first thing to do is to graph the equations, and sometimes that's the toughest thing for people. Y equals x squared looks like this. For x plus y equals 2, I'm just going to plot points. 1 plus 1 is 2. So it goes through the point 1, 1. 2 plus 0 is 2. So it goes through the point 2, 0. 0 plus 2 is 2. So it goes through the point 0, 2. So you connect those, and you get your line. So it's supposed to be bounded by the curve, the line, and the x-axis. So that's this right here, right? All right, so finding that area is a little bit awkward because these rectangles go from the curve to the x-axis. But these rectangles go from the line to the x-axis. So this is a tough problem because there's two different types of rectangles. One type goes from the curve to the x-axis, the other type goes from the line to the x-axis. You could figure out the answer to the problem this way, but it's awkward because there's two types of rectangles. So instead of doing it that way, I'm going to do it a new way. So that's the main topic of today, is this thing that I'm about to show you. So here's my bounded region. Instead of doing rectangles up and down, we're going to do sideways rectangles. And the reason we're doing that is, as you go up and down through the bounded region, so here's another rectangle, here's another one. As you go up and down through the bounded region, all of the rectangles run between the line and the curve now. So there's only one type of rectangle if you do it that way. So, but that's going to change things. So I'm going to make up some points like I did yesterday. Remember, these points that I'm about to make up are not accurate at all. I'm just making them up to make a point. Remember yesterday it was funny, I said to make 2 points. It wasn't funny 2 days in a row. Did I tell you guys that one yesterday? No. Okay, so I'm just making up these points to make a point. Okay, anyway. All right, so anyway, this point is, let's say it's 7, 2. So over 7 up 2. Like I said, nowhere near accurate. This point, let's say it's 3, 2. Again, nowhere near accurate. I don't think 3, 2 is on the curve. I don't think 7, 2 is on the line. I'm just making them up. Okay, so if that's 7, 2 and that's 3, 2, what is the length of the rectangle? 4, exactly right. So you just take 7 minus 3 to figure out the length of the rectangle. So what's going on today is, to find the length, we're taking an x value minus an x value. That's different than yesterday, because yesterday we were subtracting 2 y values to get the longer part of the rectangle. Okay, so the length of the rectangle is x2 minus x1. So that's different than yesterday. Because yesterday it was y2 minus y1. Because this distance was the height minus the height to get this. Okay, then something else is going to change. The width of the rectangle is now running up and down. Yesterday the width was running side to side. So yesterday when it was running side to side, the small width was called dx. But today it's going to be called dy, because the small width is running up and down. All right, so we've got x2 minus x1, that's the length of the rectangle. Dy, that's the width of the rectangle. And then when you multiply them together, that's the area. That's only the area of one rectangle. We've got a bunch of them stacked up on top of each other, right? So how do you add up all of those? Integral sign, add them all up. Okay, then the other thing that changes is these numbers are going to be y values. They're going to be y values because this is dy. When we had dx here, we needed these to be x values. But since we have dy there, we need them to be y values. So we're going to look at the shaded region and see how far down does it go and how far up does it go. Contrasting with yesterday where we looked at the shaded region, looked at the farthest point on the left and the farthest point on the right in the shaded region. Okay, so this lowest level is a height of what? Good. So the lowest y value is 0. And then this highest level is here. So that's at the intersection point of the line and the curve. So yeah, I know what it is, and maybe you know what it is, but just to practice the algebra, I'm going to go off to the side and solve for that intersection point. Okay, so I've got to find the intersection between the curve and the line. So this second thing says x plus y equals 2. So this one says y equals x squared. So I can replace the y with x squared. So then it'll say x plus x squared equals 2. So all I did was recopy this equation and put x squared in place of y. And that's legal because according to this equation, y equals x squared. So now I'm going to subtract the 2 over and also at the same time rearrange. And then you can factor. And so x comes out to negative 2 and also 1. Why are there two x values? This line hits this curve in two places. I didn't draw the other one because I didn't care about it. I just cared about this one. Okay, so this point is negative 2 comma something, and this point is 1 comma something. So this point is 1 comma something. How can I find the something? Well, before we find the something, why do I want to find the something? Why don't I just take this and put it here? Because that's supposed to be a y value, right? And so I can't put the x value of that point there. I'm moving from the bottom up. So I need the y value of that point, which happens to be 1, because 1 squared is 1, right? And 1 plus 1 is 2. But that's a coincidence. So I'm taking this 1 here and putting it here. This one, not that one. You know, Lee Bills was back yesterday for 7th period. And he said, I was really glad that you had the videos on Google Classroom because then I didn't miss any of the jokes. He didn't care about the calculus. He was like, I just watched for the jokes. which I can understand why. You wouldn't watch for the calculus. Everybody okay with this so far? Okay. So now the next thing we need to do is we need to get rid of these x's. It's fine to write x2 minus x1 to start out, because that's what makes sense. But then we need a y equation in there, because we're in dy. So the x2, does that have to do with the line or the curve? It's the line, right? It's the line is farther to the right in the shaded region. So that means the bigger x value is going to come from the line. We needed to take the bigger x minus the smaller x. So the bigger x comes from the line. So this x2 has to do with this equation, x plus y equals 2. We need a formula for x to plug in for that x2. So we're going to subtract y from both sides. There's my formula for x that I can put in for that x2 over there. So this is going to be integral from 0 to 1 of 2 minus y minus something, I'll figure that out later, dy. So then, of course, this x value is x1. It has to do with the curve. So it has to do with this. So I need to solve this for x, because I need to plug the x into there. So I need an equation for x. So I take the square root of both sides. Don't forget, when you take a square root, you get two answers. Do I want the positive square root of y, or do I want the negative square root of y? Yeah, that's correct, the positive square root of y, because this part of the parabola is the positive square root of y, and this part of the parabola is the negative square root of y, right? Okay, so we're dealing with that part of it, so that's why it's the positive square root of y. So we're going to minus the square root of y. So at this stage, you would do the antiderivative. Then you'd plug in 1 and 0 and subtract. If it wasn't a Wednesday, I would do that, but it comes out to 5/6. I think you know how to do that. Okay, for the next one we've got x plus y squared equals 3 and 4x plus y squared equals 0. And of course we're going to find the area of the region bounded by these curves. So after teaching this for a few years, I'm convinced that the hardest part of this for a lot of people is the graphing. I mean, we've spent time graphing in the past, but not a lot of time graphing without a calculator. So my first piece of advice is, remember you can always plot points. If you don't have any idea what the graph looks like, just make a table, x, y, plug some x's in, get some points, connect them. That always works. Okay, but we have specialized tricks for graphing as well. So for this top equation, I'm going to solve it for x. So then it says x equals 3 minus y squared. So if it said y equals 3 minus x squared, what shape would that be? It'd be a parabola, right? And would it be an upward parabola or a downward parabola? Downward, because it's negative x squared. So this is just a parabola on its side. Instead of an up and down parabola, it's a side-to-side parabola, because it's x equals 3 minus y squared. Yeah?
How do you know you're always supposed to solve for x?
You don't always know that. There are some times when you want to solve for y. If you're graphing in the graphing calculator, you need to solve for y, right? But in this particular case, it was so much easier to solve for x.
Okay.
That's why I chose to do it.
Okay.
Good question. So this is a sideways parabola. And is it pointing to the right or is it pointing left? To the left, because the y squared is negative. Okay, so this parabola starts at 3, and it's a left pointing parabola. If you had no idea that that was true, remember, if you don't know it's a parabola, you can always just plot some points, right? And in this case, I would pick some y values, like negative 1, 0, 1, 2. I'd plug those in to get my x's, and then I would just plot those. That always works. It never fails. Okay, so then for this one, this has a y squared as well, and it's also a parabola, sideways, because of the y squared. It goes through 0, 0, because 0 squared, 4 times 0 plus 0 squared is 0. And if you solve for x, the y squared would be negative, so it's a sideways parabola as well. So that one is a little bit wider, though. So there's what we get. So what's the shaded region? It looks like sort of like a shape. What does it look like? Pac-Man, or a really fat Star Trek symbol on its side, right? We're supposed to ignore the x and the y axis, right? So don't forget that. I'm going to go ahead and erase it. So there you go. That definitely looks like Pac-Man. Okay, now we have to make a choice. We now have two types of rectangles that we can draw. We can draw sideways rectangles or up and down rectangles. So if we did up and down rectangles, there'd be some that went from there to there, right? Then there'd be others that went from there to there. And then there'd still be a third type that went between the parabola and itself. So up and down rectangles, it's possible to do the problem that way, but it's awkward because there's 3 different types of rectangles. On the other hand, if you do it with sideways rectangles, they all go from the one parabola to the other parabola. So that's why sideways rectangles are a better choice on this problem. Okay, so that means that our heights are going to be x2 minus x1. And that means our widths are going to be dy. So then these numbers need to be x's or y's? Y values, because we're dy. So this is from the lowest end of the shaded region to the highest end of the shaded region. I didn't really have a shaded region, but I'm talking about this region, right? The bounded region. So the lowest end of the bounded region is here, and the highest end is there. So I have to find out where those two parabolas intersect. to find out those points. I'm going to go back to the original here. This is set up for elimination because everything kind of lines up. There's two ways to solve for intersections. There's substitution, which I did on the last problem. Then there's elimination. So what you do is you take the top equation minus the bottom equation. So 1x minus 4x is negative 3x. Y squared minus y squared is 0. And then 3 minus 0 is 3. So if I take the top equation minus the bottom equation, that's what I get. This is called solving by elimination. Then you divide both sides by negative 3. And the x comes out to negative 1. That's a little bit worrisome, right? Because don't we have two different intersection points? We only have one x value. That's because the x value for both of those are the same. To plot those points, you have to go back 1 for both of them. So the x value for that point is negative 1 something, and the x value for that point is negative 1 something. We need to figure out the somethings, right? Because that's what goes here and here. The y value of this point to the y value of that point. So to figure out the somethings, we just plug it back in to one of the equations. I'll use the top one. So negative 1 plus y squared. I'm thinking ahead with my 4 here, aren't I? Negative 1 plus y squared is 3. Add the 1 to the other side, so y squared is 4. So then y is positive negative 2. So that means this point is negative 1, positive 2, and this point is negative 1, negative 2. And then that means that these bounds are negative 2 to 2. Yes?
I have a question on the elimination. You said you take the top minus the bottom equation, but what decides which is the top?
It doesn't matter. I could have done bottom minus top. If I had done that, I would have gotten 3x equals negative 3. And then when I divided by 3, I still would have gotten negative 1. So it does not matter. And sometimes you add the equations, right? Like if this was a negative 2 and that was a positive 2, then you could just add them and they would go away. All right, so we're at this stage. Our next step is to get an equation for my x2 and to get an equation for my x1. All right, so which equation goes with the bigger x value? The one farther to the right is the bigger x value, so that's this one. Yeah, and that's the parabola with the 3, right? Not this one goes through 0, 0. So that was that one. I erased my axes, so that's kind of confusing to remember where they were, but this point, this parabola goes through 0, 0. So that's the bottom equation. This parabola is the 3. So the farther to the right, the bigger x value is that equation. I need a formula for x for that equation. Well, I already got that, right? I solved it here. So the bigger x, aka the x2, is 3 minus y squared. Just replaced x2 with 3 minus y squared. Okay, then the smaller x comes from this equation. So I gotta solve that for x. So 4x equals negative y squared. Subtracting the y squared over. So x equals negative 1/4 y squared. So then you plug that in here. So I'm going to actually go through the whole antiderivative with this just to get some practice, but we're now at a stage where it's nothing new. It's what we've been doing for a few days. A few weeks, actually. All right, so let's see. We got integral from -2 to 2 of 3 minus y squared plus 1/4 y squared dy. Then these are like terms, so I could combine them. So that's the integral from -2 to 2 of 3. That's -1 plus 1/4, so -3/4 y squared. Then take the antiderivative. So that's 3y minus 3/4 y cubed over 3. Might have been tempting to write 3x as the antiderivative, right? You with me? But since we're in y land, since our variable is y, then the antiderivative is 3y. If that was a dt over there, then the antiderivative would be 3t. And then you plug into a -2 and subtract. So that's 3 times 2 minus 3/4 divided by 3 is, I don't know why that's bothering me right now. Dividing by 3, yeah, that's going to give you 1/4. Good. So 1/4 times 2 cubed minus 3 times -2 minus 1/4 times -2 cubed. So that's 6 minus 2 cubed is 8. 8 times 1/4 is 2. Plus 2, I think. -8 times 1/4 is -2, and then yes, the opposite of -2 is +2. So that's going to come out to 6 minus 2 plus 6 minus 2, so 8. I'd like to at least set up one more. This one's going to be calculator active. So this is y equals secant squared of x, and y equals tangent squared of x, and also x equals -pi/4, and x equals +pi/4. So this is calculator active, so we're just going to graph y equals secant squared in the calculator. How do you, there's not a secant button, so how do you graph secant? It's 1 over cosine, so you'll need to put parentheses 1 divided by cosine x, parentheses squared, right, in your y1. So that ends up looking like this. Bunch of crazy parabola looking things. And then tangent squared ends up looking like this. And at first glance, we don't get a bounded region. But luckily, we've got the line x equals negative pi over 4 that cuts that off there. And then x equals pi over 4 that cuts that off there. So our bounded region is in there. So sideways rectangles or up and down rectangles? Up and down is going to be tons easier, because if you went sideways, you'd have some going from line to line, some going from tangent to tangent, and others going from line to secant. Okay, so this time we're back to up and down rectangles. So that's going to be integral and dx and y2 minus y1. The smallest x and the biggest x were given to us, right? Negative pi over 4 and pi over 4. And this will be y2 minus y1. The biggest y, is that the secant or the tangent? The secant one, so it's going to be secant squared x minus tangent squared x. And secant squared minus tangent squared is 1. That's an identity that you probably don't know, but that's okay. So since this is such, I said this was calculator active, but this is such an easy antiderivative, I'll go ahead and do it. So it's just pi over 4 minus negative pi over 4. Which is 2 pi over 4, aka pi over 2. Everybody all right?